This work is about Wi-Fi augmentation of visual SLAM algorithms. Visual SLAM algorithms have many challenges, including perceptual aliasing and computational complexity. On the other hand, Wi-Fi access points in urban environments are able to provide a rough measure of spatial locality for us. So we propose a general approach for utilizing Wi-Fi sensing in order to tackle those challenges. We augmented three well-known SLAM algorithms, including RTAB-MAP. This flowchart represents our changes to different modules of this algorithm. The following video represents the performance of Wi-Fi augmented RTAB-MAP vs vanilla version. The Wi-Fi augmented RTAB-MAP is shown in bottom right and the vanilla version is in the bottom left. The upper window shows the turtle bot in operation. The robot pauses every 3 or 4 meters, about 10 to 15 seconds, for Wi-Fi signal strength accumulation. A small window on the top right corner of Wi-Fi augmented version shows the cosine similarity between current frame and available Wi-Fi clusters. As observed, the similarity decreases as distance increases. The represented maps here show the longest collected set of frames within working memory, while most of remaining frames have been transferred to long-term memory and are not shown here. Sometimes you observe a longer map in Wi-Fi version in comparison to vanilla one, which is due to Wi-Fi immunization in our approach. If the cosine similarity between current frame and any Wi-Fi cluster is more than a specified threshold, the frames of those clusters are kept in working memory. Now the turtlebot is getting back to its initial location, and the cosine similarities between current frames and initial Wi-Fi clusters are increasing as expected. So the Wi-Fi retrieval module in our approach retrieves back all the frames within initial Wi-Fi clusters to working memory. This enables the robot to make correct loop closures, but the vanilla version is not able to do the loop closure because the respective frames are within long-term memory. Here the final constructed maps are shown. There is a double wall incident in vanilla version due to no loop closure, but in our approach the walls are adjusted on each other by successful loop closures. We tested 4 different datasets and different values for real-time threshold. If the processing time of a single frame exceeds the limit, some frames will get transferred to long-term memory. For lower real-time threshold, the trajectory error and percentage of false negative loop closures in our approach is much lower than original method, especially in larger datasets. This shows if the original method transfers all frames within some region to long-term memory, it's not able to retrieve them back to working memory when required. We are showing around 60% improvement in loop detection time while not adding much Wi-Fi overhead.